Hey everybody, welcome to the final installation in our review on circular motion. In this one, we're going to dive on vertical circles, and I think there's a few examples in here you're going to find helpful. So we're going to take a look at one that's pretty simple. We've got a girl twirling a yo-yo, and without even reading the example, I'm just going to dive in there and paste something you're going to need. So they tell us that Abigail twirls her yo-yo at a constant speed of 3 meters per second. They give us the length of the string. Okay, we can do this work. We can figure out what the force centripetal is. The big thing that I want you to notice is that, as I've done with a number of these slides, I put a question mark up here because I want you to think about where this force centripetal comes from. Again, what is the real force that actually creates the situation where the yo-yo wants to turn? So in position A, because of inertia, the yo-yo is going to tend to fly vertically. And why doesn't it do that? It's because there's got to be some inward pulling force right there. Okay, so let's just keep that in mind. When we get to position A, they ask us to draw a free body diagram of the yo-yo. That's fine, we've got it. We'll draw the downward vector for weight. A 75 gram yo-yo is 0.75 kilograms. So our weight is going to equal negative 0.75 newtons. All right, cool. The thing that you ought to recognize, though, is that mv squared over r, our inward centripetal force, has to come from a horizontal pulling direction. So just like force normal, the tension force, the string force that Abigail uses to keep the yo-yo in check, is really a variable number. It's pretty subtle. It can change. Sometimes it's big, sometimes it's small. In this case, that force centripetal can only come from tension, and I know that the tension has got to equal 1.125 newtons. Done, end of story. The tension equals the centripetal force because the weight can't help. So at position B, we need to have a force applied inward, centrally towards Abigail, so that the yo-yo again stays in check and its inertia doesn't carry it off to the left-hand side in this case. So what can supply that? Well, in this case, it's different. Because the weight points downward, it actually helps her. And what we're going to find out is that the tension is going to relax a little bit so that everything again works out so that we get the centripetal force that we are after. So let's go ahead and draw the free body diagram for that. I think we can paste that guy in right there. And what it's going to look like is we've got, again, the weight vector, just as it did before, pointing downward. We're going to add to that a tension force. And let's see. Okay, we're going to have a tension force that's going to look like that. I don't know if that's going to be bigger or smaller again than the other one, but we'll figure it out, and that's going to be labeled T. Okay? Now, what we're operating under is the knowledge that the sum of all the forces in the y direction equals m times a. And this is really where I need you to think. M times a, if we had an elevator, called on us to understand that the upward direction for acceleration was going to be positive acceleration and downward was going to be minus. It works the same way here. There's a reason why physics test teachers tend to use cardinal directions, up, down, right, and left, for the positions of roller coasters and yo-yos. It makes this part doable. So watch out for it. What's going to happen is we know that MA is equal to this number over here, 1.125 newtons, except watch what happens when I lay them out. Sum of all the forces, tension minus 0.75 newtons, equals MA minus 1.125 newtons. Why? Because this is a downward facing acceleration. The centripetal force is facing downward. Do the math. We figure out the tension equals negative 0.375. And all that means is that the negative sign tells us that, yup, tension was needed. Of course, this wasn't strong enough by itself. We needed another negative force to gang up and help create this, okay? And also the tension, because the weight was doing most of the work, is actually a smaller vector than the weight, okay? So we're going to pause it right there, squish this stuff a little bit more, and go ahead and create enough room to do the last one. Okay, and we're back. So in section C, or location C, we're down here somewhere. Let's pretend this is a circle. Tendency of the yo-yo again, flying off to the right by inertia. Abigail has to supply an upward force right here to keep this thing from happening. How's that going to go down? Well, it depends, again, on the forces that are working. So just as we had before, we're given, let's park it down here, we're given, so excuse me about that, didn't mean to do that. We're given a weight of the yo-yo that pulls down. If Abigail's going to be able to keep this thing in a circle, she's going to need to supply a force up here that's equal to positive 1.125 newtons. And so what's going to happen is that the tension is going to have to grow. It's going to not only have to supply this force, it's going to have to supply this one. So our sum of all the forces equation looks like this. Tension minus 0.75 equals positive 1.125. And when we go ahead and do the little addition of 0.75 to both sides, we get 1.875 newtons for the value of tension. Okay, again, final thing to me, take away. Tension is sort of like force normal here. It can vary. Okay, so let's go ahead and take a look at moving from that one to an actual roller coaster question, and you might see a lot of similarities. Okay, let's check it out. Okay, in considering a roller coaster question, we want to capitalize on what we just learned in looking at yo-yos. You can, again, pause the slide deck if you want to. What this one is going to do is push us towards minimal information. This is a real Six Flags roller coaster. It's one of the big loop roller coasters, 22 meters in diameter, so it's pretty substantial. You have to be going really fast around this one to make it work. And what they're asking us to do is figure out the minimum speed that riders can be traveling right up here at the top in order to keep falling. So it's a pretty typical question. We're going to start by drawing a free body diagram for people in that location. So what we've got so far in our car that's on the inside of this loop is weight pulling folks down, W equals mg. Okay, here's the thinking part. In this location, it should make sense to you that you need some kind of downward resulting mv squared over r. Force centripetal has to pull inward, meaning your guys have to be going fast enough that they require this. If this velocity is very small, then what happens is simply people fall, right? So we're operating again under the idea that the sum of all the forces on the y equals ma, in other words, mv squared over r. And here it goes. Sum of all the forces on the y, we've got 2. Here is a case where we don't have a string, but we do have force normal. So force normal is going to help us make this turn. Except force normal, if you think about it, because it's super flexible, is going to be supplied by a surface in response to us pushing on that surface. So these roller coaster cars lean in to the metal of the track. The track responds by pushing back on them. In this case, as they're rising up here, they're leaning into the track, pushing vertically. Track responds by pushing down. Our force normal pushes downward. Okay? Now, at the extreme low velocity, watch what happens. We have sum of all the forces. Force normal is our unknown. Minus mg, as we did before in the yo-yo example, is going to equal a downward mv squared over r. So what happens at the lowest speed? The lowest speed happens when weight by itself can provide the mv squared over r that you're after. And what this gives us is a really good opportunity to talk about a common physics question where they ask us what is the apparent weight of the riders. Here's the bottom line fact. Simple. Apparent weight equals force normal. So in your situation here, you will feel exactly weightless, meaning you're just on the verge of collapsing downward. And the only reason you don't is that the car has enough velocity that you require force centripetal that's equal to your weight so that you continue in the circle. Okay, so I hope that all makes sense. Cool thing to talk about. Feel free to ask. Anyway, what it lets us do is solve. We can just eliminate the minus signs now, and we have mg equals mv squared over r. And we can go after now the velocity. M's go away. We've seen this a couple of times in different situations, but velocity is going to equal square root of gr. And given these numbers, 22 meters and gravity, we get that the minimum velocity is going to be 14 and change. What is it? I got it over here. It's 14.8 meters per second. Okay, so now we're going to go and capitalize on that 14.8 meter per second velocity, assume it stays constant throughout, and see what the deal is with regards to how the forces make us feel in different locations. So let's go jump on the middle location and see what gives there. And what I think I'm going to do is go and squish this down a little bit, make some room for it, maybe tuck them down there. As we did before, the force of weight pull straight downward, right? At 14.8 meters per second, we could actually go ahead and do something useful for ourselves. And this is going to be maybe illustrative. Centripetal acceleration equals v squared over r. We plug in our 14.8, come back here, 14.8 meters per second, and we divide that by the radius of this guy, 22 meters. And I hope you're doing this along with, but whether you are or whether you're not, I hope you think about that. That's kind of cool. This is, again, a function of the fact that at the very top, at the absolute minimum velocity, your acceleration centripetal has to equal a minimum of g. In real life, they run these things much faster than that, so that force normal is called into action. But what does that look like down here? Let's go check it out. As we saw in the case of the yo-yo, there is going to have to be some kind of inward acceleration to keep the car moving around the circle in this spot right here. And where does that come from? It can only come from one place, not tension. We're not a yo-yo here. Again, force normal. So in this situation, we've got force normal, some of all the forces in the x direction. Well, there's only one of them, right? Weight equals mg is a complete y function, so it's useless to us. So force normal has to equal the mv squared over r that we need. And so what it's going to amount to is that the force normal, because we know that v squared over r equals 10 meters per second squared, this is going to lead to force normal equals mg. So what does it feel like if you're in this bare minimum situation? When you're in this location right here, you just feel apparent weight of what you weigh. Your apparent weight, your force normal, just equals mg. Okay, so that should just feel kind of simple and normal to you. So last example, you might almost see this one coming if you've been with the program here. Let's go ahead and tuck this stuff. That's close enough. And go ahead and get the last example we want to look at, which is at the bottom. Let's check it out. Okay. So in the bottom location, we've pasted a free body diagram of the roller coaster car at that spot. And we're going to think this one through. Why does the car not jet off this way by inertia? Well, because there's got to be some kind of inward pushing force that results in the force centripetal. Like we've seen before, there's no string involved here. The force normal is elastic and it's going to grow to provide the situation that we need. So we knew from before that when we added up the y forces, they equaled Fc. Let's go check out what it looks like in this case. I've got force normal here. So force normal minus mg is going to equal our mv squared over r. Now, we know from our last example we just looked at that the mv squared over r equals our weight, because of this situation up here at the top. So I'm just going to jump right to the end of that and let you figure it out. This means that at the very bottom in this bare minimum situation, your apparent weight feels like, right, factor of 2. It should feel like 2 mg, and you should feel twice as heavy as you normally would. Okay, so all that should help set us up for the very last example where we take a look at a dip and a bump on a road, really similar to roller coasters, except for the fact that they're different. Okay, so let's check it out and wrap it up together. Okay, final example. How is a hill or a dip on the road similar to a roller coaster? How is it different? First of all, how's it similar? This spot down here where Eric is supported by the meat or by the metal of the roller coaster, and he feels an upward force normal, that's exactly the same as a roller coaster. So that part's easy. This part over here, it's the same except it's opposite. So I want you to realize where you are here. I know Eric's on a roller coaster, but really he's not on a loop. He's on the outside of the loop. So what can happen is if Eric has a lot of speed, crests this hill going really, really fast, he has a trajectory. Let's grab an ink. He's a trajectory like that, and it simply carries him off the roller coaster. Well, why is that? It works like this. If he's going to maintain contact with this curved surface, he has to have some sort of inward pulling force centripetal that glues him, that expresses his m times a, that describes the fact that he's staying glued to it. Now, what real forces would create that? There's only one in this case. Force normal isn't going to help him here. What I just drew is the weight vector. The weight vector is the only thing that can help him here. Why? Because he's on the wrong side of the track for force normal to help. So see what it means. If, let's say, for example, that this, let's just go for a situation where Eric's just sitting stationary on top of this hill, then force normal actually operates this way. It pushes him up, so it's the track supporting him just like a road would support him, okay? So if we write down a sum of all the forces, it'll give us an opportunity to talk about his apparent weight and how the situation feels. All right, so let's pay attention to vectors. Sum of all the forces equals ma. Force normal at the top, let's make sure we're being clear here. At the top, force normal minus W is going to equal minus mv squared over r, or minus Fc. So if we solve for force normal, what does that feel like? Well, we add W to both sides. It feels like W minus Fc. So here's the story with roller coasters as you crest hills, but also cars as you crest hills. Your apparent weight, what it feels like, is the seat of your car pushing you up. That's force normal. It equals your actual weight minus Fc. So on a flat surface, there's no Fc, and you just feel like your weight is your weight. You apparently feel like you actually are, okay? But when you go over a turn, in order to stay glued to that turn, this Fc apparently reduces the job that your seat needs to do to lift you up to the place where if you're going really fast, this force normal just goes away and you're launched, okay? So that could come up in class if you want to talk more about it. We'll definitely be doing examples on our quiz that look like that. But we can just wrap this up by looking at the bottom situation. Here at the bottom situation, we still have a weight that pulls us down, but now the track actually can help support us. And why is that important? Because now the curvature of the track is this way, and we need to have some kind of net force, centripetal force, that's working this way. So let's just do a little sum of all the forces at the bottom and check it out. So force normal minus weight in this location equals mv squared over r, or force centripetal, except now the force centripetal points up, and so it's positive. So we solve for the force normal. It equals Fc plus W. So again, if you're on a flat surface and you don't require any Fc, then your force normal, your apparent weight, is just your weight. But if you're in a dip, what happens is the force normal will grow because the road surface can support a lot, your car can support a lot of demands on it, and the force normal will grow and give you both the Fc and your weight, and you'll feel heavy. Okay? You'll feel pushed up harder than what you weigh. Very legitimate real-life force. Final thing as a bonus, if you're still with me and you want to check it out, is this one right here. I had mentioned at the outset that lift can act like, and I think we're kind of out of room here in a slide deck, lift can act like a force centripetal as well. Here is proof positive of that. At the top, we've got an airplane's got to be upside down. Why? Because lift forces push upward when the airplane's right side up. They push downward when the airplane is upside down. And what's going on is this guy is able to execute this loop because right up here, he's just at stall speed, just under stall speed, still going really fast, 120, 130 miles an hour. And all that stuff we just talked about comes into play here as well. So we could talk about this in class if you want to. Anyway, have a great day. Hope that helped. Take care of yourself and keep on keeping on. Bye-bye now.